right. I think we are live now. Hello, everybody. Hi, Francois.
Hey, Thomas.
Welcome on my Twitch stream, and welcome all the viewers on Twitch who are here. Hi, Oleg. Oleg is in the chat, of course. And I see Alina in the chat, and I see Dav Kozak in the chat, which I presume is David Kozak. Hello. Hi, David. Yeah, so we have Francois here today. Francois hasn't been on the stream yet, but Francois is the performance lead for the GraalVM team, and he has done a lot of work related to performance and measuring GraalVM. And as performance is very core to some of our value propositions, we are putting a lot of emphasis on performance. And yeah, so this should be an interactive session. Hello, Lei CKR. It's a little bit hard to pronounce your username. Hello in the Twitch chat as well. And so if you have any questions in the chat, let us know, and I will try to monitor the chat as eagerly as possible, and I will interrupt Francois. And if you don't ask questions, then I will try to ask questions as good as I can here. And with this, we will start with only a few slides, and then we'll go into demo right after. And so let me now go to the slides here. Yeah, okay. And so Francois, take it away, and yeah, also maybe introduce yourself a little bit along the way.
Yeah, sure. Thanks, Thomas. Yeah, as you said, I'm part of the GraalVM compiler team for quite a few years now, focusing mainly on performance and tracking performance and tweaking and tuning performance. And in this session, I would like to talk about benchmarking best practices, especially because I see quite often on Twitter or other places on the internet, people trying to do JVM benchmarkings and doing some mistakes along the way. And so we will cover those aspects here.
Mm-hmm. Cool.
So yeah, there's the usual safe harbor statement mentioning especially native image is still early adopter technology. And so when we talk about performance in general, it's quite unclear what performance is, because performance is a sum of different things. So there are different metrics you may want to optimize for. There is the one that people usually have in mind when you talk about performance is throughput. And throughput is basically the time required to perform some operation or a set of operations. And for the JVM, there are a set of benchmark suites that are used in the industry or in the academia. And some of those are the DACAPO suite, the ScalaBench suite, the Renaissance suite. You can Google all of them. And basically what they do is that they have a very precise task that they want to perform. Typically, that could be compute a Fourier transform, for instance. And you will measure the time it takes to compute a given Fourier transform, and you repeat that operation many, many times. And you measure every time it takes all those different iterations. So why do it many times and not do it a single time? I'm sure Thomas knows this answer, but the obvious thing when you need to care about in the JVM when talking about performance is the warm-up effect, because the JVM has a just-in-time compiler, which will actually wait for the methods to be hot before actually compiling them. So this is the opposite of an ahead-of-time compiler, which GraalVM also has. GraalVM has both options, the native image and the just-in-time compiler. And so when you do just-in-time, then the first iterations will be slower, and then they will get faster and faster once the JVM decides to compile those methods to efficient machine code. This has some little cost. Yeah.
On this question of when the JVM decides when to compile things, like what are the approximate, how fast would a JVM compile a method typically? Like what's the typical setting there?
So you're asking basically how much time does it take to warm up?
Well, yeah, like how often would a method have to be called before it's compiled?
Yeah, so there is a magic number in the JVM which is hard coded to 10,000 at this stage,
Okay.
which means that you need to call a specific method 10,000 times before it's actually compiled by the compiler. That's the just-in-time compiler. So that has the advantage of compiling the small and often called method at the beginning. So you will keep your compiler very busy. And then along the way, you will compile the method that are less and less frequently called. And eventually you may reach a point where all methods are compiled is if you are doing the same thing over and over. But in practice, it's a bit different because you may do different operations. So compilation can happen in 6 months, even if you start your JVM now, because different code paths can be taken and stressed at
Right.
different
Yeah,
ways.
and there's also this back edge counters, right? So if a method isn't called very often, but a method has a loop inside, then it would also be compiled because it kind of counts as like how often a loop within the method would be
Yeah.
executed. Right?
Mm.
Yeah, and as one of the things I think to check is like at some point the code cache might be full, and then some of the methods might even get kind of removed again from the code cache. So some methods sometimes would then, if they are not hot enough, they would go back to being interpreted.
Mm.
And that's another thing I think to check actually if you have run into performance problems is it maybe because your code cache is too small?
There is also another aspect that can impact your performance significantly along the way is the garbage collection, obviously, because you can fill your heap and then you will need to clean it up once in a while. And I mean, the JVM ergonomics will do that for you. But we have to be careful when doing benchmarking that we do not hit the the GC right when we decide to report the final iteration, for instance. It can be 2x or 3x slower if it's short iterations, just because you hit the GC at this precise time. So yeah, yeah. On the topic of warm-up time, that's interesting. I mentioned the Renaissance benchmark suite for the JVM, and there is a university in Prague working on this one, and they maintain it, and they do some publications also on analyzing this data. And interestingly, they've noticed that even after while running the benchmark for 8 hours, even after 3, 4, 5 hours, there are still performance changes. So this means that it's very hard to say, okay, now I warm up my application. I know that it takes 2 minutes to warm up, and then I have a steady state, and I report that number. The reality is more complex, especially when you have larger workloads. So this is something fairly tricky, and basically we do not wait for warm up to be fully complete, but because it's hard to know. But what you do is basically wait for a steady state. You say, okay, now my performance hasn't changed in the last 5 minutes. It keeps reporting the same score. So I consider this my steady state. But you have to be aware that maybe 2 hours from now, you will have maybe a few percent change in performance.
Right. Yeah, and I think this is caused sometimes by this eviction of existing methods from the code cache, where the JVM would sometimes throw away machine code because the code cache gets too full, and this could mean later performance changes, even after hours and hours of the app running.
There are also some. We noticed in the Renaissance benchmark suite, there was also there's a set of Spark benchmarks, this distributed framework, and Spark internally triggers garbage collection every 30 minutes automatically. So this is something, even if you force GC or try to tweak the GC, the framework will explicitly call system GC. So that will also have an impact, and you will see spikes once in a while in your code, in your scores.
Right.
Right. Anyway, so that was about the throughput metrics. So that's basically what people usually measure and report. That's what's reported by GMH typically, or as we've seen last week with UD's talk about finding performance bugs. And he was using GMH, and you basically just you report throughput and optimize throughput by fixing the compiler for optimal throughput. But you may also care about startup time or the time it takes to execute, I don't know, 1,000 iterations. And this is where it's interesting to compare ahead of time and just-in-time compilers, because they have ahead of time obviously have a big advantage there, since they compile everything up front. They have machine code ready to be used, and they are very efficient to start up, while a just-in-time compiler has a slow startup. Then there is another concept that is very important, and I will show in the demo later, is latency. Because throughput is basically tells you how many operations per second, or the number of seconds it takes to execute something. But when you work, for instance, on a web server, you want to measure also the latency. So the latency is basically the time it takes, the delay for the answer, and not only just the executions, not the page rendering. You can do a throughput benchmark that will optimize the page rendering, for instance, but you want to know also the delays, and especially the tail latencies. Why is that important? Because if your 10% of your requests are painfully slow, that will impact the user. And if 1 out of 10 pages is super slow to render, if you look at all HTTP requests that are made when you load a web page, that can be tens and tens of requests that are made in parallel. If a few of them are very slow, that will impact your user experience. So you need to make sure that the tail latency is not too bad, and try to bring it down as much as possible. So throughput doesn't tell you that. You need to look at those two metrics, and usually you look at latency by looking at a distribution. So you say, okay, median latency would be half of the requests were answered faster than this value, and half of the requests were answered slower than this value. So median latency is interesting, but also the P90, as we call it, latency is the 90 percentile. So 90% of the requests are answered faster, and 10% are answered slower than this. So we will look at charts with this later.
Cool.
On.
Yeah. So there's one question in Twitch chat: if a performance change takes 2 hours or even 30 minutes, how likely is that to ever be reached in real-world code? I think it depends basically of how long are you deploying your services. And companies have very different strategies for that. I think Twitter is typically deploying the services for 24 hours approximately before they shut them down and restart them. Some companies deploy the services for 2 hours only and then restart it. But if you don't restart your servers, the longer it runs, the more likely it is that at some point some performance change might impact it quite substantially. And this is why I think the best thing there is to monitor very continuously, and not, because in your benchmarking environment it only goes half an hour, an hour, you might never see that change. And for us, actually, it's a challenge for GraalVM itself, because when we come out with a new release, maybe we have some issue in some benchmark that only shows up after a couple of days. So then we have to run the benchmarks for a couple of days. So there's a certain amount of benchmarking we have to do before being certain that we have not regressed, for example.
Yeah, and something that's fairly scary, I have to admit, while looking at benchmarks for the GraalVM use case, is that when we have performance regressions, it usually impacts only one benchmark or two benchmarks. So that gives you a feeling that probably the benchmarking space is not large enough, even though we run all major benchmarking suite that exist or that are common around the world, but it feels to me that, I mean, we cover only a little, very small space and try to optimize for this. So this is why it's very interesting to have customer workloads or production workloads or new technology that come out and to create benchmarks out of this, because currently it's quite surprising to see compiler performance changes that can be visible only on a single benchmark.
Right. Yeah. And internal, like, yeah, there is actually not enough benchmarks, I think, in the Java space, which was one of the reasons why we are supporting this effort that creates the Renaissance suite, where like a lot new workloads are added, because a lot of Java space is based on benchmarking of Spec GVM 2008. Which is a benchmark that was largely written in 1998. It was called Spec GVM 1998. So most of the workloads in the benchmark are about 22 years old now, and so that's why, like, when you run like modern workloads, you might not find this very representative. And for us, it's very important to be as representative as possible to like real world workloads, and that's why we welcome like measurements. We welcome like new benchmarks, like getting more data points, being more like exercising more code path is very important to complete our picture and to make sure that we are not optimizing ourselves into a corner.
There's also, in the meantime, since 1998, plenty of things happen. Typically, there are now more than one JVM language. So if you look at Scala, for instance, which is used in very large companies like Twitter, and you need to optimize for Scala because it generates very different bytecode than Java does. So this is visible when you look at stack traces and stuff like this. So it's huge, and
Right.
Typically inlining decisions you make for Scala have to be different than the ones you do for Java in the end, because Java bytecode is simpler usually.
Right. Yeah, and David Kozak asks, how does one evaluate when a benchmark is representative enough, right? So I think one way we evaluate ourselves, our benchmarks, is to see, like, are two benchmarks moving the same way if we disable a certain compiler optimization, or are they moving in a different way? So the less correlation there is between benchmark results and changing compiler configuration, the more different the two benchmarks are. And and of course we try to add things like Scala benchmarks, Kotlin benchmarks, because the bytecode patterns in those workloads are substantially different. So we try to add benchmarks from different frameworks, for example, Neo4j benchmark, Spark, Flink, and because the more likely it is that the code pattern will be different. But in general, the main thing how to figure it out is to find correlations in the measurements.
Yeah, and also when looking at when tracking performance over time, when we see that only a single benchmark is impacted by an actual performance, an actual compiler change, that's also a good indication that this benchmark reacts to something that no other benchmark reacts to. So this means that it is a good benchmark and that we should have it. And you mentioned the Spec GVM benchmarks. Those are old benchmarks, but you still want to keep those around, obviously, because you don't want to regress on those, because those are very simple workloads, usually number crunching things. And if you regress on that, probably it will be visible on others. But the larger benchmarks may only see a 0.5% regression, while the Spec benchmark may see a 5%. So that would be more obvious.
Right. Yeah, and there is a good comment in the chat. It's important to understand how well a certain benchmark suite is covering your domain of interest. And this is why the benchmark suites, they are open source. Renaissance is also open source, so you can look at each number. And you can, for example, distinguish the Scala workloads from the Java workloads. You can distinguish the Spark workloads from other workloads. And so you would then when you figure out like, oh, does GraalVM make sense for us, or like how much gain GraalVM will probably give me on my workloads, I can compare my workload with the specific workloads of the same domain that would use the same frameworks, that would use a similar language maybe, and this is then used to estimate. And this is why the geometric mean, the composite score of the benchmark suite might not be important for you, because maybe you only care about the number crunching, or maybe you only care about the Scala workloads within that benchmark suite. So that's why it pays off to kind of look at like what is the characteristics of my own program, because it allows me then to much better estimate how will this correlate to the benchmarks that are published then.
Yeah. And something we can add here is if you do not find anything that covers your space in the benchmarking world, it means that something is missing probably.
Yes.
And if you are maintaining a popular framework or have a very special setup that you think others may have to, it's good to contribute that, because if you spend half a day writing a benchmark and contributing for instance, Renaissance, it's an open source suite that welcomes contributions. So if you contribute your benchmark, then every JVM vendor will use that and to optimize their compiler for. So basically you get all the compiler experts optimizing for you. Basically, since our benchmarking space is too small, we are overfitting towards the benchmark set. So we will be overfitting towards your technology, basically. So I think if
you want a certain technology or something to run faster, contributing a benchmark to Renaissance is, I think, a very good way to go, because it will mean that on every check-in, for example, we will see the numbers on your specific workload. So yeah, so this is and that's also supposed to be the aim of Renaissance here, to really accept contributions, and we got contributions in the past there, so to make sure that like all of the frameworks are represented.
Yeah. Okay, let's try to make some progress such that I can move to the demo at some point.
Yes.
So the metrics to optimize for, so throughput, we talked about it, startup time, latency, and also resources. So resources can be CPU utilization, memory utilization, I/O if you're writing on disk or read from disk, and packaging size, which is good for the cloud era. You want to ship small binaries, and here we have AOT in mind, obviously, since it requires a smaller packaging size. Mm-hmm. Okay, so we will move to the demo. I will run a few benchmarks, and I will use some of those tools. So I have them here for reference. There are load generators. AB, it's Apache Bench. It's a fairly old load generator, fairly simple, and will give you the throughput of an HTTP endpoint, basically. WRK2 is a fork of WRK. And it basically reports the latency at constant throughput. So you say, okay, I want 100 requests per second, and it will give you the latency curve. So that's very different than AB, even though they work the same way. There's also JMeter. I will not use it here. JMeter is more interesting for very large application setup, I would say, where you have like tens and tens of endpoints and you want to stress all of them concurrently to mimic more like a production environment. So in the context of smaller benchmarking, more micro benchmarking, like I'll do here, I will not consider it. And then, so that's about the load generators. And then I will talk about some profilers. There's JFR, obviously, which is shipped with the JDK. It's just a few command line options to get a GFR dump with a very low overhead. And there's also async profiler, which is a tool I really like. It can attach to a JVM, and we use async get call trace, something like this. to get the events in similar fashion that the GFR does. Okay, that's about it. So now let's move to some terminal here and there.
All right, yes, enough slides, and let's get some action going.
Let's get something done. Yes. So yeah, we talk about Renaissance. Oops, here it is. I have it locally, so we can try to run it. Let's.
But before we run it, maybe can you go to the Renaissance website and just quickly show like what it is like.
Yeah, Renaissance.
Maybe you show the individual benchmarks. Yes, here's a lot of individual benchmarks here.
Yes, and it's compared actually against GraalVM on JDK 8 or on JDK 11. And
right, and we have the kind of, just maybe you would just put some of the workloads. There's Akka workloads, right? Or like, do we have that?
Let's go to the repository since it's on GitHub.
Right.
Okay, and here you have a list.
Right, yeah, here's the description. Yes, we have some actors.
So yes, the Apache Spark ones.
Apache Spark, database,
dummy ones, JDK streams that were added in Java 8, Neo4j, the Neo4j database. It has been actually contributed by the
Neo4j team.
Neo4j people. Actually, we had an initial benchmark in the Renaissance repo already, and they contributed the enhancements.
Cool.
And then the Dotty compiler, which is the Scala 3 compiler, which is around the corner. And this uses still an early version, but the latest version of Scala 3 will probably get updated. And some Scala workloads.
Scala things, Twitter FineAgle, which is a load balancer. Yeah. Right. Cool.
Yes. Yeah. Okay, so where was I? Okay, here. Let's run Renaissance, the FineAgle one, since I have it in my auto completion.
Right, and minus R300, what does that mean?
That's the number of repetitions. So 300 is a lot. It's just I will interrupt it.
Right, it's just running, because each iteration takes up long here.
Okay, so the first iteration took 10 seconds. So wait, before that, which JVM I'm using? I'm using GraalVM Enterprise Edition 21.0. Okay, so let's do this. Maybe we can try, so that's what I mentioned before, we can try to profile it to see what it actually does, because I think that's a critical thing in benchmarking, is that you can have numbers, sure, but if it does if the benchmark does not what you expect, it's bad. So let's go to a sync profiler that I downloaded, the 2.0 version, which is a fairly recent one. And then there is this profiler script. Profiler. And since I've done it before, you have the command already. So profile -d is the duration. So I will profile it for 30 seconds. -f is the file name. The output will be an HTML file, and this is the PID. So
the PID is the same. Is it the same, or we need a new one?
Let's look at it.
Yes,
it's 20.
This is the process ID. Yes.
Oops.
Okay.
Async with I didn't. Okay. So now it will connect to it. So
it dynamically added its instrumentation, right?
Yeah, and it said profiling started here actually.
Right.
And now we have to wait 30 seconds.
So this profiler is sampling the save points, or how does it work?
Not sure, but about the save points. But it's using the same mechanism that GFR uses,
right,
which is calling into the async call trace.
Right.
Okay, so now my profiling is done. I will interrupt the benchmarking since it gets windy in here and hot. Let's open that file. Okay, and this is my flame graph. And that's the very top of the flames. So you need to scroll all the way down. Or if you click the toggle here, it will reverse it. So we look at the flame upside down. This should be the default in my honest opinion. We've been arguing on Twitter about which should be the default lately.
Right, yeah, the flames come from the ceiling, okay.
Yes, but
this is fine.
But the spikes are less annoying now.
Okay, cool. And now we see where the time is spent. All right.
Yes, so we see the event loop here from
NO event loop. Yes.
Netty. So all of this is Netty, and here you read. So you can click on it. See channel read. You can see it here.
And that's then some Twitter code here.
Plenty of internal stuff here. Yeah.
Okay. And yes, on the right we see some GraalVM stuff, right? What is this?
Yes. So this is, if you look here, this thread. There is this thread doing some things. So it's actually two different things. Here you have the garbage collector doing things. So you can see G1 marking, etc. So it's Java 11. It's the G1 garbage collector. And here you see the hotspot compiler calling into JVM CI and running a compilation task.
So this is C++ code, not C++ code, but it's Java code ahead of time compiled, right?
Yeah.
Okay. Yeah, so this is like basically the GraalVM compiler as a native image shows up here.
Yeah. And you can see actually the time spent by individual compiler phases. So it's pretty nice. So you can you can also see what kind of optimization take most of the time, and if you want to optimize your resources, maybe you can try to disable some of them. It will probably per pricing performance.
Right. Cool.
Okay, so that's all I wanted to show about.
Can you show Can you show your script again? I missed that a little bit. Yes. So what is in this profiler.sh? Can you show it? What is in there? Just
that's part of async profiler.
That's
not my stuff, right?
I see that comes when you download the async profiler. Okay.
Yes, it's a tar GZ, and that contains the license, the README, and the profiling tool.
Right. Cool.
And yeah, you can see that I've profiled with OpenJDK2 and with GraalVM, so you can also compare the performance. And sometimes you see one of the flame being much wider. You say, okay, more time is spent on this particular flame on OpenJDK or on GraalVM, so that means that more resources are spent there. So probably the compiler could do a better job and catch up with the other and the competitor. So that's quite nice for comparison.
Yeah, it seems almost like you want a difference between flames, right?
Yeah,
an interesting feature, like a different flame graphs. Yeah.
Yeah, I don't know how that would look, but yeah. Yeah, with negative flames, right? So if you if you are faster, you have negative flames, and yeah.
Right.
Okay. So that was about Renaissance. Now I would like to move to something.
Yeah, but so in terms of what we did, right, it's like we started the workload and we waited some time so it gets at least warmed up a little bit. So we are not measuring the startup, and then we connected via this process ID. We connected to the running app, and then started the profiling there. Because I guess if we would connect immediately, we would see like a lot more compilation and a lot. And it would just look very differently because you would measure the interpreter.
And the compiler phases would be also much different in terms of CPU.
Yeah, no, that's
utilization, I guess. Because the methods at the beginning. Yeah.
Very cool tool here, the async profile.
Yeah. Yeah, big up to Andrei Pagin and the chair of the press is named the main contributor and maintainer of that tool.
Cool.
Okay, then I would like to start measuring the performance of something more complicated, because now all the Renaissance benchmarks are throughput benchmarks because they execute a task in a given amount of time. So it started at roughly 10 seconds. I think it was the first iteration. And after 22 iterations, we're down to 3.8 seconds. So it's 3x faster after some warm-up. But it's just throughput. Now there is the case of microservices or web services, or basically when you have an HTTP endpoint that can answer some requests. You do not want to look only at throughput, and you may want to look at latency, as I explained before. And you may care also about warm-up. So we will see how to benchmark one such application. So I have a little micronote application here. So it has been written by a colleague of mine, Rodrigo. If you are here, thank you for this benchmark. And basically, it's similar to the Spring Pet Clinic benchmark, much simpler. It's a shop application. So you can add clients, you can add products, you can add prices, stuff like this, and you have endpoints to store some data and to clear the cart and stuff like that. So we have this add client endpoint. I've also added this hello world endpoint that we will play with in a second. So that's...
And on the benchmark itself, would they typically create some scenario? Because I mean, now, like, one of the questions I always have here is like, well, the AB or something like these load generating tools, they typically allow you to hammer a certain HTTP endpoint, like in a very simple way. But here, for example, I would want to create 1,000 clients. I want to create like 1,000 products, for example, right? How would I do this? Would I like create some client app that is creating the scenario before I then benchmark it?
Unfortunately, yes. I think those load generators are too simple to handle this.
Right.
And the only one that can do it is JMeter. So this is the one I mentioned initially. That's typically for that kind of scenarios. So define, you say, okay, I have these 20 endpoints. I want to empty the cart every, 100 times per second. I want to create new products every minute. I want to do this and that. So you define your scenario, you click the play button, and you will measure the warm-up phase. You will measure all of it, and it will produce some report. It's more complicated to play with it. It's less intuitive and it's less easy to look at the data, but it's more interesting for very large applications.
So JMeter can do these complex scenarios.
Yes, okay. Yes. And the good point is that it also handles warm-up for you, since it's designed for the JVM. Those load generators, AB and WRK, they are not aware of the JVM, and they do not take into account the just-in-time compilation. So you need to be aware of that.
Right.
Okay, so let's look at this. So this application is right here, and I have already built it, but I can probably build it again.
Okay, so you're making sure that you have the latest jar files for that app. Good.
And now you can see that it also ships with the native image configurations predefined, which will be convenient, since it will know upfront what to do when we compile it with native image.
Okay.
Okay, then it should be somewhere in here. Yes, this is the one. So
yeah, there's one question, chat. How do you decide how many clients, how frequently things happen? Better to engineer something sensible or go random, right? I think there is no correct answer here, other than like try to be as close as possible to the scenario where you really care about performance, right? So you know, if you have a web shop or something, maybe you care about performance on Black Friday, for example, and then you would try to engineer a scenario that is closest to your Black Friday scenario, right? And I think it's really individual what you would care about. But that's why I think for real benchmarking of a web app, you need to create the example scenario that is close to what you think is supposed to model the real world. But I would think in the real world, like, people are not like lining up on Black Friday and like buy every 10 seconds, right? They typically have some bursts and there will be some random in there, right? So I think there will be a lot of random in your scenarios as well.
Okay, so let's run our
but one thing maybe about random to say here, however, is like if you generate random, like do it with a fixed seed, so you can reproduce it, so that the exact same scenario can be reproduced with the same seed, because I mean you don't want to like benchmark something that is not reproducible. There's enough non-reproducible stuff on all layers of JVM and operating system. You don't want to introduce additional sources of variability that would be from your random values. So randomize, but with a fixed seed, I would say.
Yeah, definitely. Okay, so now I have this Micronaut application. You can see that it started in 850 milliseconds, and I am on still on GraalVM Enterprise Edition here. And let's use AB to connect, to stress it.
Right, so this does 5,000 requests on the hello endpoint, okay?
Yes, and let's see how that goes. Okay, so basically it tells us, if we can scroll up a bit. Yes, we can. Okay, so it took 5 seconds to complete those 5,000 requests, and it was 950 requests per second. And it also tells you how much time was the longest request, which is 264 milliseconds. So this is a latency information, but you see that it's very, very limited. And so, yeah. Now, should we compare this with a native image? I think it's a good idea. So let's go there and compile. I already have them here, but we can, let's do something smart here because we are live.
Okay, so that's our backup native images. All right.
You never know. It happened to me once on stage.
Right, exactly. All right, so we build a native image because there we do native image and we put the jar file in there.
I put the jar file, yes. So I am build /libs/all, and this we are still on native image EE, so this will be my shopcart -EE.
All right, so this is the Uber jar that has everything in there?
Yes.
Right.
Even the native image configurations, this pre-shipped.
All right, cool. Yes, and so on the native images, like maybe we can look at the size of the ones that were generated before. So
yeah, sure. I think they're 60-ish or 70 meg. Yeah, 62 for the community edition version, and
enterprise edition is a little larger because we add more optimizations there. Like we produce more machine code for better throughput, right?
Yeah.
Right. Do you have UPX installed on your machine as well?
I don't have it at hand.
Okay.
But yeah.
Yeah, it's just with UPX you can get typically 3x lower size, which is kind of nice.
I think on that one, it even goes to 4x on this shortcut benchmark. And
Right.
the throughput impact is like
how
10%.
big is the UberChar? Can you show me the UberChar size here somewhere in the build? Right, yeah, it's 14 megabytes is the UberChar itself, right? Yeah.
Yeah.
Right, yeah. You're compiling this on a laptop, or yeah, it's a laptop, right?
Yes.
Right. Yeah.
My CPU is quite active.
Yes. Yes. So we typically recommend compiling on a beefy machine, because the image generation process is like highly parallel. And it has these two parts. The first part is already finished now, which is the analysis part. Second part now is the machine code generation part. And when you sometimes you say, oh, this takes so long, there's so much extra work done. Like if you cheat your application, a lot of this work is done in the background while you run your app. So it's kind of like compressing the work that would otherwise be done over the first hour of your application. It's compressing them now into these 1-2 minutes upfront to create the binary. It's not like we do a lot more work than is necessary, specifically the compilation parts, because later on also almost all methods will have to be compiled at some point.
The good point is that it's done only once, right? Because if you deploy your jar on like 10 machines that will do the same thing behind a load balancer, then you will redo all the compilations and they will probably do the same thing in parallel.
Right. Okay. Okay. So we have now the new version. Yes. Good.
Okay. Do you want to set some heap? Yeah. Why not?
We have the Unity EE. Yes. So we set some heap stuff. This is important, right? So you can set the heap sizes on native image. Here we set it to 400 megabyte fixed. Okay.
Yes, so it started in 15 milliseconds compared to the 800-ish that we had before. So that's significant. And now we can try AB again. Here we go. And we were at 950 requests per second, if I remember correctly. And now we're 2x faster.
Right,
in terms of throughput.
The first 5,000 requests are like served in twice the speed here, right? Because you only take 2.45 seconds now.
Yeah, to do all 5,000, and before it was more than 5 seconds.
Right, but I guess if we now like make like 1 million requests or something, at some point the cheat version might take over,
right? Yes, not by much, but yes, it will take over.
Right, but it shows you as well, like basically for most like if you don't really have a very long running app that has millions and millions of requests, like you save so much on startup with native image that even if the final throughput after 1 million requests is a little worse, you still save on CPU time. And you save on CPU time even more than you see here, because you save on CPU time of the cheat compilation that would otherwise be just running in parallel on the machine and saturating the machine's cores. So I think that's one thing to say here as well, is like when you measure the performance of a Java app, you should also consider measuring the CPU consumption as a whole to do a certain work. Not just the time it takes to do a certain work, but the CPU consumption. Or simulate it by restricting your computer to one CPU. Because often a lot of the work is maybe done in parallel and not really visible, but it's still done. And if you are in the cloud and your machine is saturated, then it will actually be something you have to pay for, and it won't be free. While on the machine that is not saturated at the moment, you might not see it. Right.
We can actually give it a try, right, by looking at the CPU utilization and memory usage of this guy by using PS record.
Right. So PS record is a tool, is a Python tool that is measuring the. I think you need to, yes, you need to put this, yeah, you need to quote it. It's a Python tool that measures the CPU consumption and RSS of processes. So we open this now.
Okay, so we can see that it took 2-ish seconds to do all of it. I haven't started right away, and then it completed all the
Right, and we
requests.
see at the beginning when you started it, there is 0 CPU consumption. There's
yeah,
like
the startup
nothing,
time is here.
there is nothing happening here. And also in the first 1.5 seconds in which we did not yet hit it with a request, the application is completely idle. And yeah, let's run now with the GVM mode for comparison, and let's compare those two graphics. Right. You can, by the way, run PS Record with GraalVM. We're gonna because GraalVM can also run Python. So we're gonna showcase that next. In the next release, we will be running PS Record on GraalVM. As you know, we like to be meta-circular, everything GraalVM. So certainly we should run PS Record also on GraalVM while it's measuring GraalVM. All right.
Okay, very similar chart, but more activity during the...
Right, and
Actually,
also at the beginning.
Let's look at the scale.
Right, at the beginning, it's similar, that there's much more activity, right? Yeah. Mm-hmm.
Yeah, and look at the... Look also at the scale of the y-axis.
Right. Well, it's yeah, it goes here.
The memory is
right.
is much lower here, because here the heap was set to did I set the heap?
No, I think you didn't set it. We need to set it as well for a fair comparison here. This is an important point, is to, like, when you measure the memory, we have to make sure that the heap configs are the same. Otherwise, you are measuring the default that would be here megabytes. Yes, that's right. 400 M. Yes, sounds about right. All right.
Okay, but still it's not so different.
Yes, it actually is not that different, because there's a lot of metadata that is loaded at the same time.
Yes. So that's the overhead of the GVM itself, not the heap.
Right. But we see here also, like, the CPU usage. First of all, we have a lot of CPU usage at the beginning in the first second. So in the first second on chit time, we have a huge CPU consumption here, whereas on the AOT time, there is no CPU consumption in the first second while we starting the app. And then even later, we take twice as long to serve the requests, but also the bars are like approximately 2x, I would say, higher, meaning we might even take 4 times the CPU consumption to serve these requests. Because it's basically the area under the curve, which is the total CPU consumption. And this is something to consider also when measuring performance or throughput here. It's not just about, you know, how many requests do I get, but like how much is my server occupied with serving those requests.
Yep. Okay, I think we are done with the A/B testing. I would like to move to WRK, if time allows, to look at latency distributions. So basically, WRK, maybe I will keep it simple since we took quite some time. I have my cheat sheet somewhere. Okay. So basically, we have this Lua script that will do a post, and we can pass this Lua script to WRK.
I see. So WRK is based on Lua, and you need to have Lua to generate the workloads.
It's not mandatory, because the script here is optional, this part. So if you just want to hit your hello world, you don't need that.
Okay.
And basically this will actually, I should do it up there and start micronode. Right.
So this has now a lot more commands. So you had to do the cheat sheet. Because what do we have here? We have this script. The script, and can you show the script? The script is, yeah, it's specifying the
it's done here.
HTTP method. It's specifying the HTTP body and the header content type.
It creates a user and it tells you that the body is JSON.
Right.
And it tells you a rate, so that's 10,000 requests per second. So that's pretty spammy.
Okay, that's a fixed rate per time.
Yes, compared to AB, because AB before you tell him upfront, like, I want to execute 5,000 requests. So now you say, okay, I do 10K per second and for a duration of 10 seconds.
Right, and I do it in 5 different connections, and I have 2 threads spamming the same.
Per connection.
Per connection, I see. So I have like 10 threads in the end.
Yes, okay. Each of them does 10K per second.
Okay, so each of them 10K per second, 10 threads, which means 100K per second over 10 seconds, which means it's 1 million requests, right?
Yeah. Okay, so let's start our app again. And
it's kind of quiet. Oh, yes, but apparently it still works.
Yes. It's quiet, and this load is probably a bit too high while I'm zooming and streaming.
Right. Okay. Then let's move the load lower, maybe.
Maybe to 1K, because it was working just fine before the demo, but I guess now it's
so here
too much.
In this type of benchmarking, it's like when you hit it with too much load, it might just
the thing that I find suspicious here is that we are in terms of seconds in the percentile, so that means that something goes
right,
very wrong.
which means that the server couldn't handle this amount of load and was starting
yes.
to... Right.
Okay, that's something more
yes,
acceptable.
That's more acceptable, right? Yeah, so this is the latency distribution, okay.
So actually what you can check is the amount of the number of requests per second here, if it matches what you've given.
Right.
So we gave 1K and it did 1K. In the previous experiment, it was too high and still 10K, surprising, but what happened? It should say somewhere that there was some issues, or maybe it could handle it, but pretty badly.
Yeah, apparently
anyway,
at the very end it was giving up, yeah. Okay, that's fine.
So basically what you can do with this, it's with the dash latency that I've added here, it gives you the full latency distribution. So you have all the percentiles. That's what I was talking about before. So if you look at the 50 percentile, it's here. It means that half the requests have been served in less than 1.2 milliseconds, and half of the requests have been served in more than 1.2 milliseconds. Right. And you can see actually the max latency is this one, is the 100% latency. It's 34 milliseconds. Okay.
Which was probably the largest garbage collection, or the first request, one of the two, right? Because here we're kind of not really warming up, right?
And it's not warmed up yet. So that's what I wanted to mention here is that this script, you need to, I mean, WRK is not designed to have warm up,
right? So we would basically want to have a script before that is warming up and then run WRK.
Precisely. Right? And this is, actually, I will cut it here.
Right.
This afternoon, I run this script on all JVM and on all native images. So basically what I do is a super stupid thing is I go into my directory and I do the exact command I just did. And I do it 5 times.
Right.
And the 6th time will be my final time. And I've double checked that actually the numbers in the 3, 4, and 5 look very similar to each other, so that we've reached a steady state. So I manually checked that. You could probably automate this, but yeah, I did it manually. And now you can look at those files. So let's see. Let's not redo all the experiments, otherwise we're here for another hour. So if we go in results. Okay, that's all. Let's do it like this. So you can see that's GraalVM EE with the 4 gig EEP. And you look at this, that's such an outcome. So you see that for the very first ping, you will get very high latency. This is because of the warm-up. But still, the median latency drops pretty significantly. So it means that you were warming up for probably half of the requests, and then it got fast.
And this is JIT mode, right? So this is JIT mode GraalVM EE, or is it with?
Yes. Yes. Okay. Yes. This is JIT, and then you can compare with the native one. Yeah, that's the exact same experiment with.
And now you open
that was a PNG.
Yes, we want this one. Yes.
This one, and here it's much better. Right. So it means that right away you got good.
You got the performance out of the box. Yes. Okay. Good. Yes. Cool. And then
so now there's another tool that is called WRK2IMG. It's a small Python package. You can do pip install WRK2IMG, and this guy takes the output of WRK and you pipe it into it, and it generates a PNG with and it will draw the latency curve for you.
Okay.
So let's see. We can try with this one. We can cat this guy into WRK2IMG and test.png, and you open test.png, and here it is. So here you can see the tail. So it's max 17 milliseconds, but still the tail latency is starts pretty late. So it's a good news. It means that most of the users
are on a 2.5 millisecond latency there. Yeah.
Even less. Yeah, 1 point something.
Right.
And very few will hit this. And you can also use --log. And it will plot maybe on a log scale.
Right.
Because usually when you look at latency graphs, the tail latency goes up like crazy.
Right. This is why you want to look at it in a log scale, so you have visibility on both ends. Yeah, makes sense.
Yeah. So actually now, if we look at my results from this afternoon, I have a file called startup, which is here. And here it is. It's not in log scale, as you can see. And here I combine the result of GraalVM, native image, CEEE, and also OpenJDK.
Right. Yeah. I think you want to look at the log scale version, right?
This is why you need the log scale, because the tail latency goes pretty high in most of the cases. And this is the startup. So it means the very first iteration. So that's what we've seen while looking at the raw files. So on GraalVM EE, it was very bad at the beginning because it was at the very beginning of the warm-up.
Right.
So that's what we're looking at here. And you can see here that this is how it looks. So here on all those curves here, green, red-ish, etc., are native images. So that's CE and EE. The CE one has a tail latency that is a bit worse than EE, but for the rest, it's all fairly similar. Interestingly, JIT outperforms already in the best throughput it gets here.
Right.
So it means that it has reached a better steady state.
Right, but already. how many requests is this for?
That was the 10 seconds. That was
the 1 million requests, right?
The 1 million, yes, in 10 seconds.
Right.
And then you can look at the very end.
Yeah, but this is important here. Is kind of like it depends. Like this graph set, like what you care about most depends on the application again, right? Do I care about after 1 million requests, how fast it is then, right? Or do I care about my latency? Like this is all application specific things you need to think about when capturing what is the best setting for your application.
Definitely. Okay, so this is the final graph I wanted to show. Is that after warm up, so after 1 minute of the execution, that's the final 10 seconds that are measured for everyone. And you have GraalVM EE 400 meg heap and 4G heap in blue and orange, and they are down here hidden actually. You can see some orange here.
Yes, so they are.
Yeah, so then you can see also the native images. And so native images have typically a worse state latency, and this is most likely because of the garbage collection.
Right, because this is
The,
with the serial garbage collector, right?
yes, in both cases. I have not done it with even on EE. So it's interesting because EE outperforms CE, even though they are on the same garbage collector. It's just that it's better code in the end.
Right.
And yeah, so but what it means here is that even after millions and millions and millions of requests, the median latency is pretty similar for everyone, and the native images are hit at the tail latency, and this can be solved by using a better garbage collector.
Yes, like
if you would zoom in here, you would
Right.
you would see also a better throughput for the JIT.
Right.
And if you exclude native images and you cut the tail, I don't have it here, but we could generate it. You would see also that EE is faster than OpenJDK in the JIT mode.
Right.
I think C is kind of similar, and then you have the native images that are slightly slower in throughput.
Right.
But yeah, basically the conclusion is that if you care about startup, consider native images. If you care about short-running applications, even short means low-load applications. It can run for a year, but if you hit it once a day with a cron job, it's perfectly fine to use a native image.
Or even if you have a couple 100,000 requests. I mean, this only starts at like 1 million plus requests here, where like then slowly the JIT versions can optimize better. But it needs millions of requests, which in most scenarios is not happening.
Yeah. Okay, so that's basically all I had. I don't know if you have
cool. Yes,
questions
yes,
or
thanks,
if there are
thanks,
questions in the chat.
Do we have any more questions in the Twitch chat? We're at top of the hour. And yeah, so we covered like benchmarking in general a little bit. We covered like load generation tools, AB, WRK2. We covered different ways to measure the latency. And yeah, so are there other questions in the Twitch chat that we should or things we should talk about? Like there was a question previously last week from a GraalVM user about GraalTune, which is our internal tool to tune flags. Maybe you just like, what is GraalTune, and like see a few sentences on
that. So basically, the GraalVM compiler has 400 plus compiler options.
Right.
And those can basically tweak thresholds of some heuristics, tell you how much you want to explore some graphs, so things like this, or if you want to enable or disable a specific compiler optimization. So basically, this GraalTune project, its idea is to play with those hyperparameters and try to find suboptimal state in the current setup. Basically, you want to tune it further and get better performance than the default configuration. And this can help you for different use case. One is to fix the compiler itself. You can find the suboptimal pattern, then you can investigate, look at the compiler graphs like you demonstrated last week, and try to find the performance problem there and fix it for good. Or maybe you notice that this is something that you don't want to touch because you will pay a big price in compilation time. For instance, if you explore super large graphs, you don't want every user to pay the price for potentially increasing your peak throughput by very little. So basically, the project is to explore this parameter space, and then
find optimal parameter values, right? And I think the challenge there is like the tool works very well, but it works better the more deterministic the workload is, and the faster the measurement of the workload is. So if you have a very deterministic workload where you can measure very deterministically its performance, and that you can run within a small amount of time, then you can try a lot of combinations, and that will then give you the better results much faster, right? Now, if your benchmark setup is not very reliable, then it's difficult to use the tool, right?
Yeah, definitely. You need something very reproducible and something that can spit numbers fairly easily.
Yeah, and this reproducibility, I think, is general the biggest challenge in benchmarking because there's so many factors like threading, like the CPU's own other occupations while you run the benchmark. Like there's so many factors in there that create noise in the system. And getting a clean benchmarking environment is like it's I think one of the biggest challenges when you want to measure some of these things. But you can test this basically by trying to reproduce your benchmarks multiple times. And this is maybe also an important thing to mention is like sometimes I saw people like writing blog posts on some performance numbers without ever like reproducing them because and that's a problem because you need to really make sure that you're not measuring noise and that you have like a dummy benchmark maybe set up as well to make sure that like you're actually not just measuring the random noise of the universe, right?
And make sure that you run the same benchmarks like 10 times and confirm your numbers and report standard deviation or confidence intervals. Because if you do not, you say, okay, this is 10% faster, but well, the noise may be 20, so that doesn't say anything. So
exactly, and it's like every benchmark, like the first question on a benchmark should be like the error bars and like did you measure it more than once? Like what's your error bar? Like when you measure it 10 times, like do you get 10 times same result or different ones? And this is something that the Renaissance maintainers in Prague, they are very like picky about, where they run like a lot of times and very long times as well. And another tip here to reduce noise that they are using, which is sometimes a little bit difficult to do, is to measure not the time a benchmark takes, but to measure some of the Intel performance counters. Because the Intel performance counters are sometimes more reliable measurements on the performance of the app. Because a certain indeterminism is introduced here just by the time component on Intel hardware.
Something else we've noticed is that you may regress or improve in one of the metrics, like throughput, peak throughput. You may get better milliseconds in the end, but you may have the opposite direction in number of CPU cycles, for instance. And this is also tricky to investigate because it's always hard to explain and requires deep investigation.
Right. But measuring CPU cycle in general, in addition to time, is I think a very important thing to do because time is just one metric here. CPU cycles taken by the processor is another very important metric. I think people should care about maybe more. And tools like PS Record can give you that. They can give you the graphs. They can also give you the raw data or like PS on Linux gives you also the raw data on CPU cycles.
Yep.
All right, cool. Thank you, Francois. Thank you for being on the stream today here.
Yeah, thank you for inviting me and sitting next to you. I haven't been doing that for like a year, so
that's right. Nice to see you. We live in the same country, but still far apart at the moment. All right. One shout out maybe to anybody who's listening on Twitch as well is we are currently trying to get applications for the GraalVM internship program that we want to expand this year. Part of the internship can also be performance related. So if you care about performance measurements, could also be a performance internship or more. We have like a lot of different internship topics. Yes, thank you, Alina, for putting it into the chat here. There is a link to internship descriptions. There's also a video. We made a video stream 2 weeks ago on the internship program that you can watch. And if you know somebody else, like a student, a PhD student, master student, who is interested in programming languages, interested in compilers, and wants to work with an international team. We have work from home opportunities everywhere. And and we do quite cutting edge stuff, I think, on compilers and VMs. So also, if you know some student, like point them to this page, please, and so we get more applications, and we can get the next generation of compiler and performance engineers going here. All right, cool. Thank you very much, everybody. This is the last stream before the Easter break, at least for me. I will not be streaming next week. I will enjoy some vacation, and I'll be back again on this stream in 2 weeks. And yeah, have a great weekend and have a great Easter holidays. Thank you, everybody, and have a great day.
Bye, everyone. Thank you.